In section 3.5, we're going to discuss limits involving infinity, and we're going to talk about the asymptotes. This would be both horizontal and vertical asymptotes. So the objective is to be able to find the limits of the function. Now I have it as x goes to plus minus infinity. That is true, of course, but we also want to take a look at other kinds of limits where x actually approaches a constant or a number, and the function may indeed approach infinity. So either way, the limits involve infinity. And these are not indeterminate form of limits. Actually, these are the limits that truly end up being, again, either the function approaches infinity or the value x approaches is infinity. It could be plus minus, either or. And then we're going to relate those to the graph of the function. So first of all, we have the epsilon delta version of the limit to infinity here, as you can see. So we're going to say the limit as x approaches infinity of f of x equals L, the limiting value. And what do we mean by this is that for every, remember the symbol here, this means for all or for every, epsilon positive, then this is the existence modifier we have, right? There exists a number n such that the absolute value of f of x minus L is going to be less than epsilon whenever x is greater than n for all x in the domain of the function. So basically, to put those words into motion, I know it's kind of cryptic, but this is what all of that verbiage means. Okay, so now epsilon, we know epsilon is very small here, right? Epsilon is a very small number. The capital N here is going to be a very large number. Okay, so think about the largest number you can possibly think of, aside from infinity. So I'm thinking, I don't know, relatively speaking, I'm thinking of a very large number, I don't know, 1 billion, good enough for us, a billion. So x is even bigger than that. So when we say that the function approaches the limiting value, that means as x gets bigger and bigger, then the function approaches that stable value of the limit, which is L. So on the graph, that means this. In this case, I have x goes to positive infinity. So notice how the function is stabilizing. Now, one thing about this is that, let's say, the function could fluctuate several times, and then ultimately what it needs to do as x gets very large, it needs to stabilize however it wants to do that. So again, it doesn't matter what it does over some interval. We're talking about way out there, right, to infinity. So this is all we're seeing, the end behavior, if you will, of the function. So we don't really care what happens in the earliest stages. Okay, so that's the limit of the function as x approaches infinity, if the limit exists. Now we can take a look at a similar situation, this time as x approaches negative infinity. That means for every positive epsilon, there is a number, call it m this time, and m is now a negative number, right? Because x is approaching negative infinity. So maybe I should put that here, where m is less than 0, m is negative, such that f of x minus L less than absolute value, that less than epsilon, whenever x is less than m. Okay, so if you think about m, again, a very small number, x is even smaller than that. So the same idea of stabilization as x gets very small of the function. So remember, with a limit as x approaches infinity or negative infinity, we're looking at the end or extreme behavior of the function actually. So not in the near term or in the near, let's say, the origin, let's say. We're not looking at something like that. We're looking at way out there in both directions. Okay, so let's take a look at our, I believe this is the only theorem we have. So this theorem reads, let R be a rational number, and R is positive here. Then the limit as x approaches infinity of 1 over x to the R is 0. And also if x approaches negative infinity, the limit of that expression again is 0. If x to the R is defined, of course. If it's not defined, then this doesn't make sense for all x. Now, to see the proof of this, I mean, you can kind of see this with numbers. For example, if I have 1 over x to, there you go, a million. 1 over x to a million. Or actually, let me not do that. That's too high. R is a rational number. 5 is rational, isn't it? Right? 5 over 1. Rational numbers, you can write them as fraction, where numerator denominators are integers. So that would count. Now, as x gets bigger and bigger and bigger, so this denominator is going to get much bigger, right? And 1 over that's going to get very small, and the limit approaches 0. And of course, the rational number need not to be greater than 1. My example I just made was x to the 5th power. It could be 1 over x to 1/2. So it's a rational number this time that is less than 1. That's still true. When x gets very large, 1 over that gets very small, approaching 0 as x approaches infinity. So how do we prove this thing? Well, I have the proof here for you. So we're going to assume the epsilon is positive, right? And I'm going to let n be 1 over epsilon. Remember, I mentioned n is a very large number. Epsilon is a small. So 1 over a small number becomes very large. To show you an example, let's say epsilon is 0.1. That's 1 over 100. So that's going to be 100. See, that gets to be large. The reciprocal of 1 over 0.01 is very large. You can think of as epsilon 0.001, 1/10,000. So now this becomes 10,000. And that's what n is. Okay, so if epsilon is positive but small, then n, which is 1 over, that's going to be very large. Now, if we look at x greater than n, for x greater than n, we're going to replace n with 1 over epsilon. Therefore, x must be greater than 1 over epsilon, which means the reciprocal of that 1 over x is going to be less than epsilon, right? And we can rewrite this expression, 1 over x less than epsilon, to mean that absolute value of 1 over x minus 0, that's still 1 over x, right, is less than epsilon. And because x is approaching infinity, we are okay to write it as with absolute value, right? So for example, if I have 1/5, that's the same as absolute value of 1/5, right? It's a positive number, so it doesn't matter. And the reason we're doing it is to make it conform with the epsilon definition of the limit, which is absolute value of f of x minus L. And indeed, that's what this is. This is f of x minus L. So it's in that form. Okay, that's the reason we're manipulating that expression. So by definition of limit, the epsilon definition that is, we just established that the limit as x goes to infinity, 1 over x, has to be 0, because that's what, again, let me just erase it, f of x minus L, it's in that construct. Therefore, the limit has to be 0. Okay? And that's not the proof of the theorem, of course, but that's just the proof of the limit of this. We established that statement. Now, what we want to do is we're going to introduce n to be a rational number, p over q. Remember, rational numbers are in the form of a fraction. That's why we introduce n like that. So if n is a rational number, in other words, and here, of course, I didn't write it, but p and q are integers. Okay, and there you have it. they're integers. Then if I write the limit of x goes to infinity 1 over x to the n, this is what we want to find, right? That limit is what we want to find. We can write it as x to p over q, and then using properties of limits, I can rewrite it in a moment. What I did from here to here, next step, is actually use properties of radicals and rewrote x to p over q as the qth root of x to the p power, right? Remember, we have x to p over q is the cube root, not cube root, it's qth root of x to the p power. That's what that is. Okay, so I'm using that property here. All right, and this is q. All right, so to find that limit, where limit of inside parentheses, a limit of something to a power is going to be, in this case, the qth root of the limit of 1 over x to the power. And we establish that limit, right? We established that to be 0. So I went ahead and replaced it with 0. So we have qth root of 0 to the p, and of course that's 0. And that is what we wanted to prove. Now this is a very important theorem, by the way. Hopefully you followed the proof, it wasn't bad. But the theorem itself, this is very important, because we want to find limits of expressions in a few minutes, and most of them going to look like that. So now let's talk about infinite limits. We just looked at limits as x goes to infinity. Now if you look at this one, you're looking at limit as x approaches c, a number, a constant if you will, not infinity. So f of x here is equal to infinity. The limit, that is, infinity. What does that mean? Well, that means for every, remember, for every n positive, it's possible to find a delta this time. Okay, the infinity is here, so we already have, it's different than what we had above. Let's just look up here, see infinity, x approaches infinity. Here x doesn't approach infinity, the function approaches infinity. Okay, so we don't have epsilon here to work with, we're talking about delta. Remember, delta goes with absolute value of x minus c less than delta in the epsilon delta definition. And that's what we're talking about here. So it's possible to find a delta such that f of x is greater than n whenever the absolute value of x minus c is less than delta. And in this case, like, what does the graph of this, like if I put the drawing like that, what would it look like? Well, this is what we mean here. X, the function now approaches infinity, and this time n is a number here. You see that? So the function actually supersedes n, and n is a very large number here again. And this is c, this is where c is, and of course we are within, this would be like delta. Okay, and in the case of equal distance on either side of c. So that's the drawing for this one. So the function actually again exceeds that large number n. That's what we mean by the limit being infinity. So remember, that means the function gets extremely large or extremely small if you look at x to negative infinity. Now let's define a vertical asymptote. The line x equal a is a vertical asymptote of the graph of a function if either of these limits work out the way I have them. Either of any one of these three limits is infinity. Okay, and again, for vertical asymptote, it could be positive or negative infinity, either way. So either the limit of the function as x approaches a approaches infinity, or x approaching a from the left, the function approaches infinity or negative infinity, or x approaches a from the right, the function approaches plus or minus infinity. In any one of those three cases, then a line x equal a is called a vertical asymptote of the graph of the function. Now I have actually a drawing for these for you, and there you have it. The case where x approaches a and the function approach infinity means that. Remember, as x approaches a, you got to consider the case where it approaches a from the right or from the left. So when we say the limit as x approaches just a, not from the right, not from the left, is infinity, then this is what it would look like on the graph. Okay, so something like x approaching, this is a, okay, there you go. That doesn't qualify, right? Because approaching a from the right, we're approaching positive infinity. A from the left, we're approaching negative infinity. Therefore, that's not the correct drawing. I'm not saying the graph could not do that, but for what I just erased in that case, then we can't say limit as x approaches a was infinity, because it was a positive from one side, negative from the other. We just simply say the limit doesn't exist. Okay. And by the way, for all three of these drawings, the limit doesn't exist, right? Just because we say it's infinity or negative infinity doesn't mean we found the number. So all of these limits does not exist, but we have more information about the behavior of the function again. So as x approaches a from the left now, so I'm coming from the left in the middle, then the function gets very large in this case. Okay, and next to that, approaching a from the right, so there you go, we approach a from the right, and the function gets very small here. Okay, so that's what those mean. Okay, and I don't know what happened, I just erased what I had. Let me put that back on there. Okay, and I think I had something like this, and there you go. Okay, now let's take a look at the horizontal asymptote of the graph. What do we mean by a horizontal asymptote? Well, the definition of the horizontal asymptote of the graph of a function is that a line y, this time, not x, remember x equal L up here, x equals a in this case. X equal a is, I didn't actually show that, but this is the line x equal a, the dotted line. This is x equal a. That's the vertical asymptote. In all three cases I have x equal a, and here x equal a. Okay, those are the vertical asymptotes of the graph. Now this time we have horizontal lines, right? Horizontal asymptotes, so we have y equal L, not x equal. So it's y equal L now. Is a horizontal asymptote of the graph of f if the limit as x goes to infinity or negative infinity of f of x approaches L. Okay. Now I have a few notes here about this, because it can get a little confusing. First note is that the graph of the function may have more than one vertical asymptote. Okay, depending on which interval we're looking at it. Good example of this is like the graph of your trig functions, like secant, cosecant, tangent, cotangent. Those have infinitely many vertical asymptotes. So that's what that note says. It is possible to have more than one over the domain. The next note is that the graph of the function may never cross nor touch its vertical asymptote. Okay, because if it does, then at that point the function is defined, right? If at a is going to have a value, so it cannot be undefined, which is infinity or negative infinity. So for that reason, a will never ever cross nor touch the vertical asymptote. The graph of a function may have no more than two horizontal asymptotes. Okay, no more than two. Two is the maximum. Okay, we can't have 3, 4, 5 horizontal. We can have 4, 5, 6, 7 vertical, but not horizontal. Because if we did, then we don't have a function. Okay. So at most 2 horizontal asymptote. I'll show you how that can be possible. And finally, the graph of a function, actually it may, doesn't have to, but it may cross its horizontal asymptote depending on the function. Okay, so remember, for vertical, never. For horizontal, it might. Never versus it may. And these are the graphs I have for you. So the first case is the fact that we have vertical asymptotes. So this is what we mean to have more than one vertical asymptote. So x equals c1 is a vertical asymptote, and x equals c2 is also a vertical asymptote of the graph, right? Now, in the case of horizontal asymptote, can I have 2 of them? Yes, the middle one. So this is y equal L1, and this is y equal L2. Okay, so those are the horizontal asymptotes. And let me, now that I change it, let me put that point is L2 and this point is L1. Okay. Now, if we look at here in this last graph, this is a case where I have a single horizontal asymptote, and I'm allowing for the graph to cross the horizontal asymptote at one point. It could cross at 2 points, 3 points, whatever. Doesn't matter. I could have, for example, a function that might do this. Several, and ultimately it will stabilize. There you go. That could be the horizontal asymptote. See, it's crossing it 5 times. But ultimately, the extreme behavior is not going to cross it, it's going to approach it. Okay, so that's what that is. Now, let's see what else about this one. Okay, this is again y equals L, where this is the L. Okay, so hopefully these will put this in perspective, and we're going to look at actually examples of some of the exercises now in a moment. Okay, let's take a look at these exercises. In all 3 of these exercises, we want to find the requested limits. Okay, so in part A, we want to find the limit as x approaches 0 from the left. Okay, so let me get my marker here, and here we go. So as x approaches 0 from the left, we're gonna look at the function. Looks like the function is increasing without a bound, right? So we're gonna call that limit infinity. Okay, and let's see, actually I'm thinking, let me see something. Okay, that's fine. In part B, as the limit as x approaches 0 from the right. Now, approaching 0 from the right, the function is approaching negative infinity, right? Now, note here, if the question said find the limit, let me write that. The limit as x approaches 0 of f of x for this one, what are we going to write? It does not exist. You see that? Because your right, your left limits are different. So that limit does not exist. Okay. In part C, the limit as x approaches infinity now of f of x. That means as x gets very large. As x gets larger and larger without a bound, well, the function is just going to keep going like this, right? Maybe not the crooked way, but it's just going to rise. So the function is going to approach infinity. We're going to call that limit infinity. In part D, the limit as x approaches negative infinity, well, on the graph is going to positive infinity. So that limit is infinity. In exercise number 4, the limit as x approaches in negative infinity in part A. As x goes to negative infinity, the function is approaching the dotted line, right? Which is elevated at 1. So that's going to be the limiting value. So that limit is 1. And as x goes to infinity, the positive infinity, again, the function is approaching the dotted line. And that limit is 1 also. Notice it remains below the line. It could, for example, I'm just changing the problem now. It could be doing this and then approaching that line. So we are allowed to cross the horizontal asymptote. Okay. In number 6, the limit as x approaches negative infinity in part A. So as x approaches negative infinity, right, means x gets very small. Well, it looks like this is looks like a cosine wave, right? That is shifted, shifted up, or has an adjusted amplitude also. Okay, but whatever that is, notice this thing is just going to keep going like that forever, right? So that limit does not exist. D, N, E. Right? It's not approaching a line. Same thing with x approaching to positive infinity. The limit does not exist. Okay? So that's how you determine these limits. Let's take a look at some more. Okay, let's take a look at these exercises. These are all from your textbook. The ones that I have circled are the ones that we're going to go through in this video. So let's begin with exercise number 10. Okay, in exercise number 10, we want to find the limit. So question number 10, we want to find the limit as x approaches 1 from the right of x plus 1 divided by 1 minus x. Okay, now we want to do this, by the way, without graphing. Okay, the graph could help us actually with the argument or the discussion that we have, but we really want to do this through either analytical or by using correct judgment. Okay, so now as x approaches 1 from the right, okay, the numerator clearly approaches 2, right? So that's not a problem. The trouble is in the denominator. Notice right now it's in the form of 2 over 1 minus 1 is 0. 2 over 0 is undefined, right? Now, it is not an indeterminate form, by the way, but I just want to mention that if we have a number division by 0, which is undefined. For us, in terms of limits, that means the answer is going to be either infinity over negative infinity. Now, because we're approaching 1 from the right, so if you look at the denominator, for example, negative 1.1, 1 minus, and x would be 1.1 coming to right from the right, coming to 1 from the right, that is. So 1 minus 1.1 is going to be negative 0.1. Okay, again, let's say 1.2. So you can kind of see as we approach 1 from the right, the denominator is going to be negative, right? So we have a positive numerator, negative denominator. Therefore, the quotient or the ratio is going to be negative. Therefore, the number division by 0 here yields negative infinity. Okay, and that's the answer to number 10. Let's take a look at number 14. In exercise number 14, we want to find the limit as x approaches negative 1, again from the right, of 1 over x minus 1 over x plus 1. Now, in number 14, again, if you plug in negative 1 in the first fraction, we get negative 1. In the second fraction, we get 1 over 0. Again, 1 over 0 here, that's going to be undefined, right? So we're going to argue again the same way. The question is, do I have positive or negative infinity? Now, coming to negative 1 from the right to negative 1. So here's number line 0. This is negative 1. We're approaching negative 1 from the right. So that means we got values like negative 0.9, negative 0.99, and so on. So the fraction is going to be what? It's going to be 1 plus these negative numbers. So the fraction is going to be positive. True? So as x approaches -1 from the right, this is going to be 1 over -1, right? But the second fraction approaches infinity, right? So it's going to be in the form of 1 is positive, and we just established denominator is positive. The fact that we have 1 over 0 makes this undefined. So it looks like the fraction approaches infinity, so we have like -1 minus infinity, that kind of a limit. Now, of course, how are we going to do this? The answer is going to be -1 minus infinity, doesn't matter. So this answer is going to be simply -infinity. All of the limits, well, in this section, most likely end up being either infinity or -infinity. Most of them, not all of them. So it depends on, again, how they make these up. So let's take a look at, we did number 14, now number 18. In exercise number 18, we have the limit as x approaches 0 from the right of cotangent of 2x. For number 18, so we want to find the limit as x approaches 0 again from the right of cotangent. Okay, now for this one, you're welcome to look at the graph, but we don't want to do this by graphing, okay? Because some of these graphs, like look at this one, are not our standard functions, so we know readily the graph what it looks like. And remember, in general, we don't determine limits from the graphs unless the graphs are so clear that we can do so. So what do we need to do here? I'm going to go ahead and rewrite this cotangent as the ratio of cosine to sine. Okay, that helps me understand it better. Now we're going to do it kind of like we did the earlier ones. We're going to argue whether the numerator is approaching something, and we'll see what happens. So as x goes to 0, cosine approaches 1, sine approaches 0. So 1 over 0, now question is, does it approach infinity or -infinity? That's what we need to know. Okay. Now, the numerator, as x goes to 0, cosine 2x, right? As x goes to 0, and let's say this is the graph of cosine 2x. So the point being, the numerator, as x approaches 0, it approaches 1, right? The numerator approaches 1. The denominator is 0, so that's the one we need to really worry about. As x goes to 0 from the right, the denominator approaches 0, but it approaches 0 through positive values, right? Through positive values. Therefore, in this case, we're going to call this limit infinity. Okay, so that limit's going to be infinity, again, because we're approaching 0 through positive values, both on top and on the bottom. Let's take a look at number 22. Number 22, we have 2x squared minus 1 divided by 4x squared plus 1. So let's do that one. In number 22, the limit as x approaches infinity, actually, no, number 22 didn't approach infinity. Yeah, it did. Of 2x squared minus 1 divided by 4x squared plus 1. Now the denominator, of course, is positive, right? Because you're squaring. The numerator is also positive. So now this is in the form of infinity over infinity, right? As x approaches infinity, this is an indeterminate form. Indeterminate form. Okay, so one of several indeterminate forms. So for these, we need to work them out. Okay, argue wouldn't help here. And also, let me mention this because some students have had calculus before, and immediately they recite Hopital's rule, and they say, well, we'll just solve it with Hopital's rule. Well, we don't know about Hopital's rule at this point, so we have to do it the way that we've learned so far in this section and in this course. So I'm going to rule out Hopital's rule and do it algebraic method. Okay, so what we need to do is we're going to divide the numerator and denominator by x squared, everything by x squared. So it's going to be negative 1 over x squared and 4 plus 1 over x squared. And see that? Numerator and denominator. So from now on, we're going to be using most likely this limit. So let me recall what this limit was. 1 over x to the r. Remember this one? As x approaches infinity is 0. So we're going to use this anytime we want to find the limit of 1 over x to a power. But it's important x has to approach infinity, okay, for this limit. And it's not x approaching a. So consequently, I can say, well, that limit is 0. That limit is 0. So what are we going to end up with? We're going to end up with 2/4 or 1/2 limit of a constant. As x goes to infinity, limit of 2 is 2, limit of 4 is 4, and the result is 1/2. And there we have that limit for number 22. The next one we're going to look at beyond 22 is number 28. Okay, so let me write down number 28 for you. Number 28, we want to find the limit as x approaches infinity of parentheses 1 plus 1 over x, and then times x squared plus 1 divided by x squared minus 1. Okay, so for number 28, we can actually now write this as limit of a product is product of limits, right? So we can write it as limit as x goes to infinity of simply 1 plus 1 over x times the limit of x squared plus 1. I don't need parentheses on that anymore. Okay, so that's just going to be the limit of x squared plus 1 divided by x squared minus 1 as x approaches infinity. Now, because of the theorem that we just mentioned, that limit is 0. And within this first limit, the limit of a sum is sum of limits, so that limit is 1. 1 plus 0 is 1. Times, now, for the second limit, let's actually do what we just did in number 22. So I'm going to divide the top bottom by x squared, 1 over x squared. Everything divides by x squared as x goes to infinity. And again, we have a case where that limit is 0, that limit is 0, and therefore the limit of the fraction 1 over 1 is going to be 1, and that whole thing is 1. So the answer to number 28 is also going to be, not also, but it's going to be 1. Okay. Let's see, did number 28, and let's take a look at number 36. Okay, the limit of the trig function x over 3x plus cos x. In number 36, the limit as x approaching infinity of x divided by 3x plus cos x. Okay, so this is going to equal to, now at this point, as x goes to infinity, we know cosine of x, right? As x goes to infinity, cosine x is not defined, right? Because it fluctuates as x goes to infinity, so it doesn't come to a value. So we need to work this out some other way. So I'm going to go ahead and did what I did with the other exercises. I'm going to divide by x and write it in the form of cosine x over x. Remember earlier we addressed the cosine of like sine x over x, so this time we're going to look at cosine x over x. But this is easier than sine x over x. Now this limit as x goes to infinity. Now the limit of cosine x over x as x goes to infinity. We know the numerator, right? The numerator is going to fluctuate between plus minus 1, right? The values, right? As cosine fluctuates between 1 and negative 1. So the numerator is a constant fluctuating between positive and negative values, right? Let me write that. Cosine of x is going to be bounded between 1 and negative 1. Okay, we know that. Now, but it's going to be a constant, right? Positive, negative doesn't matter because we're dividing by x as x gets very large, so you have a number divided by, let's say, infinity. Okay, so that value is going to approach 0, correct? So that value is going to approach 0, whether it's positive, negative, doesn't matter, it's going to approach 0. And this limit is going to be, so I can just write it here, it's going to be 1/3, because now that approaches 0. Okay, and there is the answer to number 36. And let's take a look at now number 50, 54, 56. In exercise number 50, the question here reads, find the horizontal and vertical asymptotes of the graph of a function. Do not sketch the graph. Okay, so we don't want to do that. We want to use the definitions of horizontal vertical asymptotes. That is their limit definition to do that. And we are going to do number 50 now. Okay, in exercise number 50, we want to find the limit as x approaches infinity of x over x plus 1. Now, this limit is going to be what? Again, in its raw form, it's infinity in the numerator, infinity in the denominator, right? So that is an indeterminate form. So I'm going to divide the top and the bottom by 1 over x. This limit is going to be 0, so the whole limit is going to be 1. Okay, because the limit is equal to a constant as x goes to infinity. This is the very definition of a horizontal asymptote. So the horizontal asymptote is going to be y equals 1. Remember, horizontal is going to be y equals 2. Vertical is going to be x equals 2. And that's what that is. Now, for a vertical asymptote, because the question again said find horizontal vertical asymptotes. For vertical asymptote, we're going to look at division, place where we get division by 0, right? So notice here, x cannot equal to negative 1, right? Not in the domain, and that means at that point we have a vertical asymptote. And this is HA. Now for vertical asymptote, we're going to look at the limit as x approaches a number. Okay, x must approach a number, a value, not infinity. And that number is going to be negative 1. Okay, or the point of discontinuity. And of course we're doing it for x over x plus 1. Okay. Now this limit, again, we're going to argue this because we are approaching negative 1, and we're going to approach negative 1 from the right. Okay, negative 1 from the right in this case. Okay, let me read the exercise number 50. Yeah, horizontal vertical asymptote. Yep. So coming from the right, that's going to be coming from the right. So the values are going to be actually like, I don't know, negative 0.9, negative 0.99, like that. So the denominator is going to be positive. The numerator is going to be negative, right? And that means this limit approaches negative infinity. Okay, so we do have a vertical asymptote. Now why didn't I go from the left? He could have done that. Limit as x approaches negative 1, this time from the left. Now as we approach -1 from the left, because we still have division by 0, doesn't matter. Now coming from the left, I'm looking at numbers like -1.2, -1.1, like that. And when you add 1 to these, you get negative numbers, right? So that's going to be -0.1. The point being this is going to be less than 0 or negative. So this time now, the denominator is going to be negative. The numerator is going to be negative, right? Whether you approach -1 from right or left, the numerator is just x. It's going to be negative. And this time it's positive infinity, right? Equals infinity. So either way we get, as long as the limit, remember for vertical asymptote we said the limit as x approaches a from the right of f of x, limit x approaches from the left of a of f of x, these should give you plus, minus, infinity, either or. Okay, and in this case we did. So we don't have to do both. You don't have to do both as long as you show the limit is either infinity or negative infinity. So we do have a vertical asymptote. The vertical asymptote is going to be at x equals -1. And we already established the horizontal. Okay, that was number 50. Now we're going to take a look at number 54. In number 54, this time we want to find the limit as x goes to infinity of, as x approaches infinity, of 2 minus x squared divided by x squared plus x. Okay, so for horizontal asymptote, again, we're going to find the limit itself. So that's going to be, we're going to divide top bottom by the highest. Usually what we know, how do we know what to divide by? You divide by the highest exponent in the expression. So if I have 5 plus x to the 6 and x plus 3x to the 8, you divide the top bottom by x to the 8. So you get 5 over x to the 8 plus 1 over x squared, and x over x to the 8, see the highest exponent, 3x to the 8 over x to the 8. And the limit as x goes to infinity, here's 0, here's 0, that's 0, and this is 3, so this is 0 over 3, and that's going to be 0 if this is a limit. Okay, so there's a quick sidebar, an example of a limit. We'll save that for you. Okay, so I'm going to do the same thing then. I'm going to divide everything by x squared. So this becomes 2 over x squared minus 1 divided by 1 plus x over x is 1 over x. I mean, x over x squared is 1 over x. The limits of the fractions in this limit are going to be 0, so that's going to be the whole thing. The limit is the horizontal asymptote. Y equals -1 over 1 or -1. So we do have the horizontal asymptote. The HA is going to be y equals -1. Okay, we have that one. Now for the vertical asymptote, we got to find the values where denominator is undefined. Okay, division by 0. So in other words, if I look at x squared plus x, factor it, you get x plus 1. Two numbers make this 0, right? So x equals 0 and x equals -1. Therefore, I'm going to do this. I'm going to find the limit as x goes to 0 of 2 minus x squared over x squared plus x. Okay, and then separately we got to find the limit as x approaches -1 of the same. Because again, for those two numbers, the division by 0 is undefined, and we have some kind of a vertical asymptote. Now, we just need to show that this limit individually, either infinity or negative infinity. We don't have to do both, just as long as you do one or the other, it suffices. So first, let's look at x goes to 0. Now, we're going to look at, again, you can look at x going to 0 from the right or from the left, doesn't matter. So I'm going to change that to limit as x goes to 0, let's say from the right in this case, of 2 minus x squared over x squared plus x. Now, as this goes to 0 from the right, the numerator is going to be what? 2. The numerator is 2. 0 from the right, well, x squared, that's going to be a positive. And 0 from the right, so that's like 0.1. So the denominator is going to be positive, right? So the fraction is positive over positive. It's like 2 over 0 kind of thing. So it's going to be positive infinity. Now, as x goes to 0 from the left, the 0 from the left, that's going to be negative, right? Like negative 0.1. But then here you have negative 0.1 squared, which is going to be less than that. So it's going to be negative infinity. But again, all we need to establish is either positive or negative infinity. Therefore, because the limit of f of x is equal to infinity as x goes to 0 from the right, that would imply that we have a vertical asymptote, and the equation of it is x equals 0. Okay, that's one. Let's do the limit as x goes to negative 1, and I'm going to make this negative 1 from the right or left, doesn't matter. Limit x goes to negative 1. And again, we can make it go from the right, okay, or left, from the right. So the numerator, negative 1 squared is going to be positive 1. 2 minus 1, the numerator is going to be positive, right? Now, the denominator, negative 1 from the right means like negative 0.9, something like that. When you square it and add 1 to it, right, this is going to be positive, plus 1 remains positive. So that limit is infinity. Okay, and that's good enough. We just established the limit is infinity. Again, limit negative infinity would have been just fine if this is what it had turned out. So x goes from negative 1 from the right is going to be of f of x is going to be infinity. So this would imply there is a vertical asymptote at x equals negative 1. Cool. So the graph of this function is going to have two vertical asymptotes, one at 0 and one at 1. Okay. And we can graph it again, use decimals or something to establish the graph and see what the graph looks like. Let's take a look at the last exercise. This one would be number 56. Exercise number 56 is, the function is f of x equals 2x cubed divided by 3x to the 6 plus 2 and square root of that. This one is a little tricky. Okay, so let's see. Notice the denominator, by the way, is never 0, right? The denominator is never 0 for this one, for number 56. So there is no vertical asymptote. In other words, the domain is all real numbers. So this would imply no vertical asymptote. Now we got to work on horizontal asymptote. For horizontal asymptote, let's see, we're going to look at the limit as x goes to infinity of the function, right? Now, as x goes to infinity, and we're going to look at the case where, for instance, what if x is positive or negative, right? Because it makes a difference. Doesn't make a difference here, right? because the denominator is always positive, but it makes a difference whether x approaches whether x is positive or negative, right? Because if it's negative, numerator is negative. If it's positive, numerator is positive. So we're going to look at this limit if, let's say, x is positive for now. Okay, so when x is positive, let's see, because we need to find this limit right now, by the way, this is an indeterminate form, because x cubed, as x goes to infinity, approaches infinity in the numerator. In the denominator, forget the 2 and forget the 3, right? I know I see 3x6 plus 2. I know that's what that is, but really the underlying function that dominates is that. Forget that, forget that. So the question is, well, what is that limit as x goes to infinity, right? Well, square root of x to the 6, first of all, what is the square root of x to the 6? Now, going back to our algebra days, that's going to be, because we're looking at the principal root of that, it's going to be absolute value of x cubed, isn't it? That guarantees that the answer is going to be positive. And this, we can write it as, it's going to be x cubed for x positive, and it's going to be negative, actually, x cubed, right? If x is negative. So that's how we can write it without the absolute value. So I'm drawing inspiration from what I have just written here. Therefore, for our denominator, then, the case where x is positive, we have the indeterminate form, infinity over infinity. The case where x is negative, we have indeterminate form, infinity over negative infinity, right? So how do I resolve these? The indeterminate forms must be dealt with. Okay, so how we're going to deal with this is we're going to actually do this. We know that, again, square root of x to the 6th is going to be x cubed. That's provided x is positive, right? So now we can actually manipulate this. I hate the sound of that word. Manipulate sounds like you feel guilty for doing something you're not supposed to be doing. But that's okay to manipulate this one. Okay, so what I want to do is actually, I'm going to divide everything by x to the 3rd. So that's going to be 2x cubed over x cubed, and in the denominator we're going to have square root of 3x to the 6 plus 2 divided by x cubed, right? Now somehow I need to incorporate in the denominator that x cubed with x to the 6. So why don't we take advantage of that expression? And I'm going to rewrite this limit as limit x goes to infinity of, in the numerator it's going to be 2. In the denominator it's going to be square root of. Now I'm going to move x cubed within the radical. So it's going to be 3x to the 6 over x to the 6 plus 2 over x to the 6. You see how I move that x cubed inside? X cubed outside square root becomes x to the 6 inside. See, right here, we have that here. So that's the form I used. Good. And when we do that now, that's perfectly fine. Now we can actually take this limit. This limit is 0, and the one next to it is going to be 3. So the answer is 2 over square root of 3. Isn't that cool? And of course we can rationalize it. Usually in algebra they tell me I should rationalize, so I'm staying with the rules of the game. Okay, so there we have it. Here is the horizontal asymptote. We just showed the limit as x goes to infinity is that. So this becomes horizontal asymptote y equals 2 root 3 over 3. But that's just one for now. There may be another one, or it may be the same one. We need to look at the case where x is now going to be less than 0. Okay, and see how this is going to go. So I'm going to do that for x less than 0 now. We're going to find the same limit. okay, when x is less than 0. Now here's what we need to note though. Remember in here what I had here? If x is less than 0, then negative x cubed, you write it in square root as x to the 6. Okay, but it's got to be negative x cubed, right? So square root of x to the 6 becomes negative x cubed if x is less than 0. And I'm going to do that. I'm going to say that that is absolute value of, again, x cubed. And because x is less than 0, this will be negative of x cubed. Good. So we're going to divide the numerator and the denominator by that. Limit as x goes to infinity of, again, the expression is 2x cubed over negative x cubed by square root of 3x to the 6 plus 2 divided by negative x cubed. See how that works? Now, when we push that negative x cubed in the denominator, when we push that inside the radical, we're going to have to write it as root x to the 6. Okay, so this is going to be 3x to the 6 divided by x to the 6 plus 2 over x to the 6. And in the numerator, we have negative 2. Now we can use the theorem. The limit of 1 over x to the r is 0 as x goes to infinity, and this other limit is going to be 3 next to that. Okay, so we have negative 2 divided by square root of 3, rationalized. It becomes negative 2 root 3 over 3. Aha, here's the second asymptote that we have. So there are actually two horizontal asymptotes of this one. The horizontal asymptotes are y1 equals 2 root 3 over 3, and the second one is negative 2 root 3 over 3. And there you go. Okay. And we can actually graph this. I'm going to graph this one for you in Desmos so you see what it looks like. Just to make a believer out of you. Okay. And that's number 56. Very elaborate. Okay. So let me actually go graph it and then I copy it in here for you. We'll talk about it in a moment. All right. So here's actually the graph of the function in exercise number 56. I just did this in Desmos. Okay, you can clearly see those horizontal asymptotes, and of course I looked at the extended domain in Desmos, and this line is indeed y equals 2 over root 3, and this other line down here is y equal negative 2 over root 3. That's how I graph them, which is negative 2 over root 3 is about 1.5, negative 1.5, that's where that is. And the other one is about 1.5 up here. So you kind of see again the graph behave however it wants to behave, right, over this domain between, let's say, 2 and negative 2 and 2. That's how it's doing. Whatever you want to do, but the extreme behavior, if you will, the graph is approaching a ceiling and approaches a floor that is given by those two equations. Okay, so just wanted to take a look at the graph of this function. But anyhow, with that, we are done. Very interesting section at that. And we are good. We are through with this section 3.5.